Hello everybody, and welcome to this video. This video is going to be a little bit shorter than the other videos, but the material that's covered in this video is going to be quite important. We'll be covering section 1.3, Propositional Equivalence. Before we start, an important type of step used in mathematical argument is the replacement of statements with another statements with the same truth value. And that's what we're going to see in propositional equivalence. Because of this, methods that produce propositions with the same truth value as a given compound proposition are used extensively in construction of mathematical arguments. Note that we will use these terms, the compound propositions, to refer to an expression formed from propositional variables using logical operators such as P's and Q's and so on, or P and Q, P or Q, and so. So look at this definition. A compound proposition that is always true no matter what the truth value of the proposition variables that occur in it is called a tautology. Here's a new terminology that we have learned, a tautology. So any propositional statement that is always true no matter what the values of the variables are is called a tautology, and the opposite is called a contradiction. So if you have any propositional statement which can always be false no matter what the values of the variables are, is called a contradiction, and anything in between that is called a contingency. A simple example for this could be, take this statement P or not P. P or not P is always true. How do we know that? Just look at the truth table. So let's make a truth table. So let's start with a truth table with a column dedicated for P, and we'll start with true and false, the different two values that P can take, and let's identify what not P is. Not P, of course, is going to be the opposite, so false and true. And let's see P or not P. Let's calculate the column of P or not P and see what we get. So true or false is always true. False or true is also always true, right? And hence we see that this statement is always true no matter what the values of P is, and hence this is considered to be a tautology. Another example is P and not P. P and not P in this case is always false, so P and not P is considered to be a contradiction. How do we know that this is always false? Let's look at the truth value again, or the truth table, and see. So we got P and not P. I'll just copy the table here to the other side, false and true, and let's calculate P or not P. Sorry, we want to calculate and. Let me just erase that. And okay. So we got and of course we know that true and false is false, false and true is false. So there you go. No matter what the value of P is, this is always false, and hence this is called a contradiction according to our definition here. And going back to the previous example, this is always true, and hence this is called a tautology. So now that we've looked at the definition of tautology and contradiction, let's look at logical equivalence. A compound proposition, according to what's written over here, okay, that have the same truth value in all possible cases are called logical equivalences. And hence the definition. Look at the definition. The definition says the compound proposition P and Q are called logical equivalent if and only if Q is a tautology. So here's the condition. If you have two compound statements, and if you can prove that the if and only if you apply if and only if among these two, and that comes with tautology, then both compound propositions P and Q are considered to be logically equivalent. And this is the notation that is used to prove or to indicate the logical equivalence of two statements. Now here I want to mention that I'm going to stop the notation abuse that I've been using for the past 2 or 3 videos. Now that we have a strong definition of the symbol, the equivalence symbol over here, I'm not going to abuse this notation anymore throughout this video or the next video that are coming. So now one way to determine the whether two compound propositions are equivalent or not is using the truth table, as we've seen previously. And of course you can always apply this definition or use this definition to determine whether two compound statements are logically equivalent or not. So here's the example. Let's look at the example number 2, and let's try to determine whether these two are the two compound statements given here, not P or Q, and the second proposition, the second compound statement, not P and not Q, whether they are logically equivalent or not. Now, as I said earlier, just a few moments ago, that the truth table is the best way to find out whether two statements are equivalent or not. So let's use the truth table over here, starting with P, Q, 2 columns dedicated for P and Q. So true, true, false, false for the values of P, true, false for the values of Q. And now we need to find the truth values for both statements. So let's look at the first statement. The first statement is not P or Q. This means I have to calculate P or Q first, and then I have to calculate not P or Q, and this is going to be my column identifying the truth value for the first statement. And for the second statement, I need to calculate not P, and I need to calculate not Q, and then I need to calculate not P and not Q, and basically I need to compare these two columns together to assert whether the two statements are equivalent or not. So let's do this exercise very quickly. P or Q will give us true, 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 false. If you recall, this is the truth table for the OR operator. True or true is true, true or false is true, false or true is true, false or false is false. So the negation of that would be false, 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 true. Now let's calculate the not P column. The not P column is going to be false, false, and false is going to turn to true. The not Q is going to we're going to invert this column over here, so this will be true. True will turn into false, false will turn into true, and false here and true here. And now let's calculate the not P and not Q, and we end up with false and false is false, false and true is false, true and false is false, true and true is true. And of course you will notice, let me put this in, highlight this with a different ink, you will notice that this column is exactly like this column, and hence we can say here, therefore not P or Q is logically equivalent to not P and not Q. And in fact, this formula here, the two formulas that are shown in table 2 are called the Demorgan Laws, and basically it through Demorgan Law, you can negate a compound statement that is built using the AND operator or the OR operator. Now, moving on forward, we can apply the same thing with logical statements that have more than two logical variables. So here's an example, example 4. It says, show that P or Q and R and P or Q and P or R are logically equivalent. Now, this is called the distributive law of disjunction over conjunction. If you recall, in regular algebra, we know that multiplication is distributed over the addition operator. Simple example would be, say if you have 3 multiplied by 2 plus 5, this can be written as 3 multiplied by 2 plus 3 multiplied by 5, right? Because and this is how the distributive law is defined. The same way in propositional logic, we've got this example shows the distributive law of disjunction over conjunction. Now, this is a law already known because I've already checked the truth table, but for a person who's just starting with this, you cannot come to a conclusion that this distributive law is going to work unless you make sure that these two are logically equivalent. Now, to have these two logically equivalent, let's build a truth table for 3 variables. So we've got variable P, so we'll have a column dedicated for P, another variable Q, and the third variable is R, so we've got 3 columns dedicated to those. And let's start with the truth values of P. Now I need to create all the possible combinations of truth and false for these 3, and the best way to do it is have 4 true values and 4 false values, false, 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 dedicated for variable P, and then we alternate every 2, so you got true, true, false, false for the first one, and then alternate again, true, true, false, false, and then here we alternate one, true, false, true, false, true, false, true, false, and there you go. We have now through these different values, I can assure that we've covered all the different combinations of trues and false for these 3 variables that can exist for these 3 variables. Now let's look at the first part of the question. The first part says P or Q and R. So let's calculate Q and R first. Q and R. So we'll have a column for Q and R, and then we need to calculate for the whole. So we're going to have a column for P or Q and R, and this would then cover the first statement. And for the second statement, we need to calculate P or Q, and we need to calculate P or R, and then we need to calculate for the whole thing. So we need to calculate for P or Q and P or R. So let's do that. Now Q or R, let me just rewrite it in a better way. Q or R. For Q or R, so we've got T or T, true, T or T is T. T or false, sorry, my mistake. It's not Q or R, it's Q and R. So true and true is true, true and false is false. And then the next one is going to be, whoops, the next one is going to be false again, and the next one is going to be false, because false and false is false. True and true is true. And then we've got false, false here, and false here, because remember, for the conjunction, the value is true only when both of them are true. So now we're going to calculate P or Q and R. Q and R, Q and R is already calculated over here, so we're going to look at these two columns. This is the first column that we're going to look at, and this is the second column we're going to look at, and we're going to OR it, or calculate the disjunction of it. And true or true is true, true or false is true. So we got true here, another true here, and we've got true here, and then look at the remaining of the values. False, it's all false over here and all false over here, so we're going to have false, false, false for the for all the last three values. Now let's go for the next one. P or Q. P or Q is just the OR table, and for the OR we have true, 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 because one of these values is always true here, is true here in all of these combinations. Okay, and we're going to have two true values here because we have one of these is true in this combination and the rest is going to be false. Now P or R, it's going to have this, we're going to calculate it the same way. So whenever there is one true value in any of these two columns, we're going to have a true value here. So you got true, 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 true. And let's look over here. True, false or true is true. False or false is false. False or true is true. False or false is false. And this is the second last column. And now we need to look at these two, these two columns, and calculate the conjunction between them. And we end up with true, true, because we got true values all the way, and we've got another true value here, and then the rest is going to be false, because no matter what, no matter if one value is false, then the whole result is false. Now just look at the result over here and the result over here, and you will notice that they are equivalent, and hence we can say therefore P or Q and R is logically equivalent, 1, 2, 3 lines, with P or Q and P or R. And hence we can conclude that this, we call this the distributive law, okay, of the disjunction, of the disjunction over the conjunction. And now that we know that these two are logically equivalent, later on we can use this equivalency to build more complex statements, logical statements. Another logical equivalence that is very important, that is very important and extensively used in our text and very useful, is the equivalence. The equivalence that is shown over here, which is, let me just identify this, P implies Q is logically equivalent to not P or Q. And let's use the truth table to prove this, and then we'll have we'll add this this logical equivalence formula into the bag of formulas that we can use later on to prove equivalence or solve equivalence problems. So let's use the truth table. So the question is, prove that this is logically equivalent. So excuse me. So let's try to prove that using the truth table. And of course we start with P and Q as two columns dedicated for each, and then we are going to calculate, or let me write the truth values for them. We got true, true, false, false for the P, true, false for the Q. Then we need to calculate P implies Q, and we need to calculate the right hand side, which is not P or Q. So first we have to calculate not P, and then we'll calculate not P or Q. and we need to compare between this and this to see whether the two are equivalent or not. So P implies Q, as we know that it is true, false, true, true. This is from the first video, which covered section 1.1. Please go back to that if you have any doubts about the results of this column. And let's start with not P. Not P is just the opposite of what we have here. So you got false, false, true, true. Not P or Q is calculated by using this column here and this column here, and we end up with, because this is the OR operator, so it's going to be true unless both of them are false. So not P or Q is going to end up being true, false, true, and true. And just notice, let me use the red ink, just notice that this column and this column is equivalent. Hence we can say, therefore, P implies Q is equivalent to not P or Q. And there you go. Here's another formula. So let me just point out here that this is another formula or a rule that we can put in the formula bag. Speaking of formula bags, here let me show you the textbook has made a table of the most common formulas that are used in logical reasoning. And table 6 over here shows the logical equivalences, or several equivalences with its name. And allow me to invest a few moments to go through these formulas so that we get familiar with the different formulas that are available in the formula bag. And I would really recommend students in this course, or whoever is working in logic propositional logic, to memorize these formulas with their names, because they're going to be very useful as we go further in this material. So as I said, I'm going to spend a few moments over here to go through these formulas, and these are logical equivalences. And by the way, if you don't trust the textbook, or you don't trust me, you can always go and use the truth table method to prove or to verify the equivalences that are given in these tables here. So in addition to the previous two formulas that we saw a little bit earlier in this video, we also have a law called the identity law. So basically, P and true is equivalent to P. P or false is equivalent to P, and that is the definition of an identity law. If you recall, in regular algebra, the identity for the addition operator is 0, because when you add 0 to any value, you get the same value. The same way, the identity for the AND operator is true, because when you AND it with any variable, you'd get the same variable. Excuse me. Now, the same way, the identity for the OR operator is the false value, because when you OR any value with the false, with that identity value, you'd get the same value. And in the same way, if you go into regular algebra, the 1 is the identity for the multiplication operator, okay, and we know that 0 is the identity for the addition operation. You can it's always in propositional logic, you can always have an equivalency, or you can see a pattern, an equivalency pattern between the concepts that we are familiar in regular algebra and the concepts that we're going to take in propositional logic over here. Now, in the same way, the domination law says that one value is always going to dominate for a particular operator. So P or true is always true, no matter what the value of P is. And the same way, P and false is always false no matter what the value of P is. And that is the same that's the same case with let's say if in regular algebra, if you multiply any number with 0, you're always going to get 0 no matter what that number is. So as I mentioned earlier, you can always find a pattern of similarity between concepts in numerical algebra or regular algebra and the concepts in propositional logic over here. Now let's go forward. So the next two laws are called the idempotent laws. So P or P is equivalent to P, and P is equivalent to P. The next law is called the double negation law. So the negation of P is equivalent to P, and the double negation law is similar to the negative value or multiplication with -1 in regular algebra. You know that the negative of any number is that same number, so negative of -5 is 5. So this is the same thing. Now then you have the commutative law. The commutative law says P or Q is equivalent to Q or P, and the same way P and Q is equivalent to Q and P, and this is equivalent to in regular math or in normal algebra, this is as if you're saying A plus B is the same as B plus A. So the same way, if you go and look further, the associative law is similar to the associative law in regular algebra. So in propositional logic, the associative law says that P or Q or R is equivalent to P or Q or R, where on the left hand side the first two are done before the second operator, and the right hand side is done on the right hand side, the right part is done before the whole expression is computed. So the same way, the associative law is defined also for the OR operator. So you've got P or Q between parentheses or R is logically equivalent to P and let me go back. I've been mixing the operators. So P and Q between parentheses and R is logically equivalent to P and between parentheses Q and R. The same way with distributive law, and we've seen one of these in one of the previous examples. So we know over here the first law says that P or Q and R between parentheses is equivalent to P or Q and P or R, and this is exactly similar to, or this pattern is very similar to the distribution of multiplication over addition in regular algebra. Now here's an interesting operator. Here's an interesting logical equivalence that is hard to it's hard to find an equivalence in regular algebra. It's called the Demorgan Law. So the negation of P and Q is equivalent to the negation of P or negation of Q, and the negation of P or Q is the negation of P and negation of Q. So all you need to do is just flip the middle operator over here and negate both sides. So the AND is flipped into an OR with the negation of both variables, and in the other one the OR is flipped into AND with the negation of both variables. The absorption law is also another law that can be used, and the absorption law says P or P and Q is equivalent to P. And this absorption law is for the AND OR combination. That there is the OR and AND combination, and there is another one for AND and OR, the AND and OR combination, which is also equivalent. And of course the negation law, and we've seen the negation law. We've seen the truth table for this negation law in a previous example in this video. So P or not P is always true, and P and not P is always false. So these the table 6 over here covered the two basic operators, the conjunction and the disjunction, and it listed down several different laws or logical equivalences that involve these two operators. Let's go to table number 7 and table number 8. Table number 7 and 8 basically list those logical equivalences which are concerned with the other two logical operators, namely the implies operator and the if and only if operator over here. And of course, it is, as I said earlier, it is going to be very helpful if you memorize these formulas so that we can solve logical problems easier and faster in later stages of these video series. So let me go through these formulas and spend a few moments just to make you familiar with these formulas. So P implies Q is equivalent to not P or Q. This is exactly this is one of the examples that was covered a few moments ago, and if you recall, I said that we want to add this into our formula back, and there you go. This table lists that equivalence. Next, P implies Q is logically equivalent to not Q implies not P. And this is the formula that we have covered, I believe, two videos ago in section 1.1, if I'm not mistaken. But nevertheless, here this formula is also a very useful formula that one can use as a tool when solving logical questions. The next formula is P or Q is equivalent to not P implies Q. Next one is P and Q is equivalent to not, and P implies not Q in parentheses. And the same way with not P implies Q is logically equivalent to P and not Q. Now, if you want to double check and make sure that these equivalences hold, you can always go and use the truth table. Now, the same way, you've got these more complex compound statements. I'm not going to read them, but basically you get the idea of how important these small pieces or tools can be for us when we solve logical problems. Table 8 lists the logical equivalence involving the bidirectional statement. So in this case, P if and only if Q is logically equivalent to P implies Q and Q implies P, and this is basically the definition that is based on the definition of the bidirectional statement, which we have taken in section 1.1 or covered in section 1.1. And in the same way, we've got 3 different formulas that involves the bidirectional statement. I would really recommend that you memorize these tables very well, so that it will be easier for you to solve problems later. Now, I need to pause over here and discuss an extension to the Demorgan's law. The associative law for disjunction shows that this expression P or Q or R, okay, is a well-defined. So it's a well-defined expression. Okay, in the sense that it does not matter whether we first take the first disjunction or the second disjunction, or whether we take the first 2 disjunctions first, or compute the last 2 disjunctions first and then compute the whole value. Okay, if we take the first disjunction and then take the disjunction of with R, or we take the second disjunction first and then we take the disjunction with P, the values are going to be the same. So if we extend this, we can say that because this is well formed, we can say that if we have several proposition values, say P1, P2, or P3, or until we have, say, Pn. So if we have n different values, then this is also well formed. This means that it doesn't matter whether we take the first disjunction and then take the result of that and do the disjunction with the third one and take the result of that, or we do the opposite way, which is we take the last two disjunction and then we calculate disjunction of that with the one before it, and so on. So the logical value is always going to be the same. This is also well defined, and the same way we've got P1 and P2. So, and if we have n different logical variables, it's the same. The same thing is true here. This is well defined. Whether you calculate it by taking the first two pairs and then pairing them up this way, or you take the last pairs and you pair them up this way, the logical value for this is also going to be the same. Now, extending this idea, we can define the extended Demorgan Law, which says that negation of P1 or P2 or Pn is logically equivalent to the negation of P1 and negation of P2 and the negation of all the P's, and the last P, which is P of n. And this follows the pattern over here follows the similar pattern of the simple Demorgan Law, which we covered in here. As you can see, where is it? The Demorgan Law here. There it is. So as we said, in the simple Demorgan Law, we flip the operator. If it is an and, it is going to flip into or, and if it was or, it's going to flip into an and. The same way in the extended Demorgan Law, basically the operator is flipped. So if for the or, it becomes an and all the variables are negated. The same way we can define the Demorgan Law for multiple variables with the and operator. And of course, here the and is going to flip into an or, so we're going to negate P1 or, and then negate P2 with an or, and then we or it all the way to the last variable. Well, going a step further, let's look at example number 5. Example number 5 says, use the Demorgan Law to express the negation of these two statements. Statement number 1. The first statement says, Miguel has a cell phone and he has a laptop computer. And of course, we're going to come to the next statement later on, but let's cover the first one. So let's write let's identify the different components. So we can say that let P be the statement Miguel has a cell phone, and Q would be the statement Miguel has a computer. Now, in order to apply the Demorgan Law, let's first of all rewrite this whole statement. Let's call this statement capital S1, which is this statement here. Okay. So here we can say that this is statement S1 is written as P and Q, because we have an and operator here. Now we apply the Demorgan's Law. When we apply the Demorgan's Law, we get not P and Q, and if you recall, not P and Q is logically equivalent to not P and not Q, as I said, not P or not Q. I seem to keep confusing or mixing and ors together, so I would really recommend that you follow with me, and if I make a mistake, just note that down, that whatever I'm writing is probably logically more correct than whatever I'm saying, because I tend to mix the and the or a lot while I'm talking and recording these videos. So now let's now that we have applied the Demorgan Law and we found out that this is the negation of the logical statement, let's translate this back into the English language. And not P in this case basically it means that it's the negation of the first statement. Now there are two ways of doing that. One is the mathematical way, and the other one is the English language or English expert way. So I'm going to apply the definition using the mathematical way. I'm going to just apply the negation definition directly. So this would be equivalent to, or can be written as, it is not the case that, and P, of course, which is Miguel has a cell phone, C-E-L-L, phone. Okay, and we'll translate this into or, and not Q. Not Q is, according to the definition, it is not the case that Miguel has a computer. Now we can go further and we can oops, got a rogue screen here. Now we can go and translate this into regular English, and for translating into regular English we can simply say that Miguel does not have a cell phone, or he does not have a computer. Now we can do the same thing with the second statement, and the second statement here is saying, let me bring it into the screen. The second statement says Heather will go to the concert, or Steve will go to the concert. So let me just put a line over here and identify a variable called R, and R would be Heather will go to the concert. Okay, and S, small s of course, is going to be Steve will go to the concert. Okay, and let me call this a statement capital S2 as statement number 2. So in this case, statement number 2, because we have the OR operator, oops, rogue screen again, because we have the OR operator, we can write the statement like so. Come on, we've got S2, capital S2, can be written as R or S, and when we apply, then we apply the Demorgan Law. So not R or S is logically equivalent to not R and not S. And let's convert this or translate this into the English language. Not R is, I'm going to, as I said, apply the definition directly. You can then change it into regular English. So when I apply the definition directly, I'll say it is not the case that, not R, R is Heather will go to the concert and apply the operator, and it is not the case that Steve, yes, Steve will go to the concert. And here is the negation of the original statement using the Demorgan's Law. And of course you can rewrite this by saying Heather will not go to the concert and Steve will not go to the concert, and that will also be logically correct. Right, with this covered, now we've come to the most important part of this video, this part of the lecture, which is the method of constructing new logical equivalents using the logical operators, or the equivalents that we have taken so far. So let me scroll back to these formulas, or the formula sheet, or the formula bag that I've discussed earlier. So we're going to use these formulas that are given in Table 6, Table 7, and Table 8, and we're going to see how we can construct new logical equivalences using previous ones. So here's an example. Let's take this example and see how that can be done. The example says, show that not P implies Q and P and not Q are logically equivalent. Now in mathematics, when you try to prove that in regular algebra, when you try to prove that two expressions are the same, what do you do usually? If you're given a left-hand side and you want to make sure that it is equivalent to the right-hand side, what do you do in regular algebra? In regular algebra, you either start from the left-hand side and then you apply some algebraic rules until you reach to the right-hand side, or the other way, the other strategy is you start with the right-hand side and then you apply some algebraic rules until you end up and you reach the left-hand side. So you got two strategies. Strategy number one is starting from left-hand side and reaching to the right-hand side. Strategy number two would be starting from the right-hand side and reaching to the left-hand side. A third strategy can also be done, is that you start from the left-hand side, okay, you start from the left-hand side and you reach to some common expression, and then you do the same thing with the right-hand side. You start with the right-hand side, or you take the right-hand side and then you bring it to that specific expression, and this is the third strategy that you can use to prove that the two expressions are equivalent in normal algebra, and the same thing you can do here in propositional logic. So now, putting these strategies in mind, let's see which strategy can be useful for example number 6. In example number 6 says that prove that these two are equivalent. So let me rewrite that. It wants us to prove that not P implies Q is logically equivalent to P or not Q. So let's identify this as the left-hand side, and let's identify this as the right-hand side. Now we can use one of those strategies. So let's apply strategy number 1 and see if it takes us anywhere. So we can say that left-hand side is basically not P implies Q. Okay? Now, this, according to, if you recall, there's a formula, let me write over here, there's a formula that says P implies Q is equivalent to not P or Q. Remember, this was one of the examples that I have covered earlier. Let me take you back over there just to refresh your memory. I think it was here, yes, towards the end. Remember this formula over here, P implies Q is equivalent to not P or Q, and I said let's put this in your formula bag, so that we're going to use it, and luckily enough in this example we are using it. So we're going to basically, not is going to stay as is. Whatever is inside the parentheses is going to be substituted with not P or Q because they are logically equivalent. Okay, so we can write over here, which formula did we use? We used the P implies Q equivalent to not P or Q. So this is the formula we used. Let me just put this aside for going from this step to this step. Now look over here. This is inside the parentheses we have a complex expression, and we want to negate the whole thing so we can apply the Demorgan's law. So if we apply the Demorgan's law, we'll end up with not P, and this is going to flip from an or to an and we'll have not Q. So what did we apply over here? We applied the Demorgan's law to get to this step. Now let's see what can we do further. Notice we have a negation and a negation, so here we can apply the double negation formula. So when we apply the double negation formula, we end up with P and not Q. What did we apply over here? We applied the double negation. Okay, and basically look over here, P and not Q is the right hand side, so we can say which is equivalent to the right hand side. And there you go. As you have seen, we have used this strategy number 1, where we started from the left hand side, we applied some logical expressions, and we ended up with the right hand side. And this is the answer to example 6, and this is the way that we use to prove logical equivalencies between two expressions. Now keep in mind that you could have used the truth table to prove the logical equivalencies, but of course using truth table is equivalent to, like, kindergarten counting, and using these formulas to prove the equivalency is like the more advanced way, more high school way of approaching this these kind of questions. So now let's go to the next example and see, which is a little bit more complex example, and see how we can apply the formulas to show the equivalency of the two statements. So here the equivalency of the two statements, let me rewrite this into mathematics. So basically I'm asked to prove not P or not P and Q is logically equivalent to not P and not Q. Okay, so I'm going to identify this as the left hand side, and I'm going to identify this as the right hand side, and I'm going to now choose one of those strategies. So let's start strategy number 1, which is starting from the left hand side and seeing whether we can reach to the right hand side or not. So let's start with the left hand side. The left hand side is not P or not P and Q. Okay, now this can be logically equivalent to what? Now notice, let me change the color of my ink. Now notice, this part can be considered as a term, and this part can also be considered as the second term. Now in this case, I can apply the Demorgan's law, which is the negation of the first term and the second term. Don't look at this complex expression. Just think of it as a single term, just a single term. So here we can say that we got a term or another term needs to be negated, so we can apply the Demorgan's law. So in this case, what I can say is that let's apply the Demorgan's law. So it's going to be not P, negation of P, and we're going to flip the operator here, so it's going to be and then not whatever is inside the second term over here, which is not P and Q. So there you go. What did we apply over here? We applied the Demorgan's law. Now this can be written as equivalent to, now let's try to let's try to see what we can do. Not P, I'm going to leave it as is, and leave it as is. Look at this part here. Let me change the ink. Look at this part here. It's the same thing. Now here we can apply the Demorgan's Law again, right? So let's apply the Demorgan's Law. So we'll end up with what? We'll end up with not P, and we're going to flip this into an OR, and not Q. So we apply the De Morgan again. Now keep in mind that it is very useful, especially for you if you want to during your revision for exams or assessments, and it's also useful for the person who is correcting your exam papers to list down what formulas have you used to go from one step to the other. This takes the ambiguity out and the guesswork out of a person who's reading or revising this text, and it also takes the guesswork out of the correction phase if somebody's correcting your exam paper. Right. So now this is I can safely say that this is equal to not P, and now the not P is basically a double negation, right? So this ends up with P or not Q. So which formula did we use over here? We used the double negation formula. Okay. Now after that we can safely say that we got not P over here, and then we've got another expression inside the parentheses with the OR operator. And if you recall, the second distributive law says that the AND can be distributed over the OR. So let's apply the second distributive law. So we'll have not P or P, not P, sorry, and P. There you go. I've messed up again. As I said, I always mix up my ANDs and ORs. So please, if I do mix up, whatever I'm writing on the screen is the one that you should take, not whatever I'm saying. Okay, so we end up with not P and P, or because we're using the distributive law, or we end up with not P and Q. So which law did we use over here? We used the distributive law, and specifically the second distributive law. Remember, if you recall, let me take you back over here. If you recall, we've got a couple of distributive laws. So here's the first distributive law, here's the second distributive law. So basically we're using the second distributive law. So let me write over here, second distributive law with an A. Okay. Now let's continue. Now I'm sure you must have recalled that not P and P is always false, right? So this is going to be completely a false. So this whole thing will reduce to false, and we're going to leave the rest as it is, not P and Q. Which law did we use over here? We used the law not P and P is equal to false. Now this law also has a name. Now if you do not remember the name, you can just write the law that you have used in this column over here. Let me take you back to the table to see what the name for this law is, and you'll see that this is the negation law, the second negation law, not P and P equals to false. If you do not remember the name second negation law, you can just write whatever law you've written over here to remove the ambiguity for anybody who's correcting the paper, or even for anybody who's reading what you have written so far. Now, next what I'm going to do is I'm going to just rearrange this. So I'm going to write P, not P and Q, or F. Now I didn't rearrange it just because it looks pretty. No, I rearranged it because I applied a formula, and that formula is the commutative formula for the disjunction. Now let me take you back to the table and show you. Look over here. Where is it? The commutative law. The commutative law says that you can flip the positions of the variables with the OR and the AND. Okay, so many people usually think that this is being done just so that for aesthetic purposes because it looks pretty, but that is not the case. I mean, although we are rearranging it for our convenience, but that rearrangement is basically based on a specific law. If this law did not exist, then that rearrangement would have not been possible. And basically, this commutative law is also available in regular, in normal algebra, and that's why you can, flip the positions of the variables from one side to another of the operator. Right. Continuing with that, now anything or false, we know that is the same thing because that's how the identity law is defined. So we can apply the identity law. Let me take you back to the table to show you the identity law. Here's the identity law, and the identity law says that anything or false is that same thing. So the false basically, just as we say in algebra, flies away or disappears, or and so on. So if you come over here, we've got something or false is that something according to the previous law. So we end up with not P and Q. Which formula did we use? We used the identity formula. So the identity law for F. And if you notice that this is basically the right hand side, so we can say this is equivalent to the right hand side, and hence we have proven that these two are logically equivalent. So as you can see, I have used the first strategy, which starts with the left hand side, and then applying some logical steps we arrived at the right hand side. And this is another demonstration of how you can use the first strategy to prove the equivalence of two logical expressions. Right. So now let's continue with the next example. This example says, show that P and Q implies P or Q is a tautology. Now, if you recall, let me take you to the definition. The first definition we've taken in this video series is the definition of tautology. And basically, a tautology means that the compound proposition statement is always true no matter what the values are. It's always true. So I can rewrite this question by saying that the question is asking me to show that P and Q implies P or Q is always true. And here I can identify the left hand side and the right hand side. Now you've noticed that I can use strategy number 1, which is going from the left hand side all the way reaching to the right hand side, or I can use strategy 2, which is starting from the right hand side going all the way to the left hand side, okay? Or I can do strategy number 3. But notice strategy number 2 is of no use over here. I mean, it's going to be very difficult to start from the right hand side and then come to this. So I'm going to so I believe that strategy number 1 is the best strategy to use over here. So let's start with the left hand side. The left hand side is equivalent to P and Q implies P or Q. Now let's see, what can we do over here? Now, if you recall, in one of the formulas in our formula bag that I mentioned earlier is, let me scroll down to that. Yeah, here it is. P implies Q is equivalent to not P or Q. So I'm going to apply that here. So we've got P implies Q, or say this implies this. This can be rewritten as not first part, which is P and Q, or the second part, which is P or Q. Now, which formula did I use over here? I used a formula. Let me go back to the formula bag and see whether the formula has a name. We look over here. P implies Q is equivalent to not P or Q. It does not have a formula. No problems. We don't need the name anyway. I can say that P implies Q is equivalent to not P or Q is the formula that was used to reach to this step. Now, the same way. Now what do we do here? Look, we've got not for this whole thing, or negation for this whole part, so we can apply the Demorgan's law. So Demorgan's law says not P, flip the operator to an or, not Q. Okay, so this is the Demorgan's law. Everything stays the same. So I'm writing over here, Demorgan was used for this step. Now, I can easily say let's do rearrangement because we got or, okay, but that is not entirely true. Although we can do the rearrangement, but the reason that we can do rearrangement is because the associative and the commutative laws of the disjunction. So we'll use the associative and commutative all together, and we can end up with not P or P in one, and then or not Q or Q in the other. So I've used over here what? The associative and commutative laws for the disjunction. And this is what I use to reach to this step. Let's go further. And I'm sure you must recall that not P or P is always true. If not, let me just take you to the table again, and you'll see that, whoops, you'll see that not P or P is always true. So we end up with what? We end up with true over here, or not Q or Q is also true. So we end up with true over here. And this is from the negation law, or you can just write it not P or P is always true. This is what we have used for this, and we end up with true or true is always true, and this is by the domination law. Domination law, LAW. And let me show you a glance of the table here. The domination law, where is it? The domination law over here. So basically anything or true is always true, and that's what we end up. And there you go. We have started with the left hand side and we reached to true. True is the true value. True is the right hand side. So basically the first strategy worked. I started with the left hand side and I applied some logic steps until I reach the right hand side, and therefore we can say, therefore I'll write it in red over here, P or Q implies P and, sorry, I did a mistake again. P and Q implies P or Q is T, which means it is always true, which means that we can rewrite it in English saying that P and Q implies P or Q is a tautology. Is a tautology. Working on my spellings over there. So there you go. Here's the answer to example 8, where we prove that one expression is a tautology. And I want to repeat here again that you can do the same thing using the truth table, but the truth table is for kids. Using these formulas, using these equivalence formulas, is for more expert grown-up people. The last topic that we're going to cover is propositional satisfiability. And basically a compound proposition is satisfiable if there is an assignment for the truth values to its variables that make it true. So if you find any combination of truth values that makes the whole compound proposition true, then we say that this proposition is satisfiable. When no such assignment exists, then we say that this is not this is unsatisfiable. In other words, when the compound proposition is false for all assignments of truth values, no matter what combination we use, then we say that the compound proposition is unsatisfiable. It helps to note that a compound proposition is unsatisfiable if and only if its negation is true for all assignments. So we can write over here, if compound statement is unsatisfiable, okay, if and only if the negation is true for all assignments, is a tautology. So here's a handy formula or a rule that you can keep in mind. So when we find a particular assignment for truth values that makes a compound proposition true, we have shown that it is satisfiable, and that's what we are going to see in this example here. Now, if we can find such a combination of truth values that satisfies the a special expression, then we say that this truth value is the solution for this particular satisfiability problem. Now, the satisfiability problem is very similar to the equations in regular algebra, because satisfiability in algebraic equation means finding a solution. So if you can find a value, say if you have an algebraic equation with x, y's, and z's, so if you find specific values for x and y and z to satisfy so that the equation is solved, then we say that these specific values is the solution. So it's the same thing here. So if you have an expression such as the ones that you see in front of you over here, and these, if you can find some kind of a combination of truth values that satisfies it, then you are actually you have actually found a solution for this expression. Now, to show that a compound proposition is unsatisfiable, let's see, other way around, okay? If you want to show the other way around, we need to show that every assignment of truth value to its variables makes it false. So it's not easy to prove the unsatisfiability, but satisfiability is easier to prove. But this is going to be more clear when we look at this example. So let me change my ink to black, and let's see what this example says. The example says, determine whether each of the compound propositions, this is the first proposition, which is this lengthy expression over here. This is the second proposition. And the third proposition is basically the conjunction, okay, of the first two. So let me just rewrite them to make it easy to understand. So statement number one, capital S1, is basically defined as the first statement, P or not Q, and Q or not R, and R or not P. And statement number two would be the second statement, which is P or Q or R, and not P or not Q or not R. And the third statement is statement number three, which is basically the conjunction of statement number one and statement number two. So we want to first see whether statement number one is satisfiable or not, and we want to see whether statement number two is also satisfiable or not. So let me change my my ink to red, and let's look at the first statement. Now notice the first statement has this part here, the second term here, and the third term here, and we've got the and operator or the conjunction between them. So you've got and here and you've got and here. So it is very clear that in order for S1 to be true, we need this and this and this, all three of these to be true. Now, if you look at these, you would notice that, so we can say here that this is true, okay, when we got P, Q, and R have the same value. The same value. There you go. So now notice, so if they have the same values, you've got false. So let's say if all values of P, Q, and R are false. So in this case, we'll get what? False or not false, which is true. False or true will make all of this is to true. The same way here, false and the negation of that, if false or true, is true. This and the same can be applied to the third one. False or true is going to be true, and hence we'll get three true values: true and true and true. Will make the whole statement true. Now the same argument can be done for the true value for all the three variables P, Q, and R. Excuse me. So now we have come to the conclusion that statement number 1 will be true only if P, Q, R have the same values. Now let's look at statement number 2. Now notice that statement number 2 has two parts with a conjunction operator in the middle. So in order for statement number 2 to be true, we want to have this part to be true and this part to be true as well. Now inside here we've got the OR operator. Inside here we also got the OR operator. So this means that statement number 2, I'm going to write over here, statement number 2 is true, okay, when at least one of the values P, Q, and R is true, and at least one of them is false. So and this is very apparent, this is very clear, because if at least one of them is true and one of them is false, this the Oaring of these three values will produce a true value for this part. And the same way here, when you negate one, we negate the values, so the true will be false and false will be true, and Oaring them will also produce a true value for this one. So now we know that because of this, S1 is satisfiable, so we can clearly or easily say that therefore S1 is, capital S of course, is satisfiable. Okay, and with this we can say that S2 is also satisfiable. Alright, now let's look at the third question. Now S3, which can be written as logical equivalent to S1 and S2. Now is it satisfiable? Well, if you can, from the reasoning here, you'd see that S3 is not satisfiable. Is not satisfiable. No, the reason is very simple. Now look over here. We have got two parts with a conjunction. Now in order for S3 to be satisfiable, we want S1 to be satisfiable and S2 to be satisfiable. Now S1 is satisfied if what? S1 is satisfied if all of them have the same value. Now if all of them have the same value, then S2 cannot be satisfied, because S2 is satisfied only when we have at least one to be true and at least one to be false. So if we try to satisfy S1, S2 is not going to be satisfiable, and if we satisfy S2, then S1 is not going to be satisfiable. So in both cases, we're not going to end up with a true, for both values. If we're not going to end up with true for both values, then this means that well, the conjunction of this is going to be always false, and hence S3 is not satisfiable. So there you go. We've started with logical equivalence. We've seen, we have constructed or seen a bag of logical equivalence in this video tutorial, and then we have seen how we can use that logical equivalence bag of tools or bag of formulas to do construction of new logical equivalences by proving the equivalences of two or more logical expressions. And then we've seen how we can build arguments for the satisfiability problem of in propositional logic. Wow! In the beginning of this video I said that when this video is going to be a short one, but evidently, as you can see, it turned out to be that the concepts in this video were quite important, and it took some time for us to explore it. So before ending the video, I would like to advise you again to please go to the textbook and solve the exercises. And believe me, the exercises basically cover the exact topics and concepts that was covered in this video. Have fun, and looking forward to see you in the next video.